I'm going to start recording then. Good morning, everyone, wherever you are. Now, I'm starting a little bit early today because I wanted to make an announcement, and I also wanted to um, finish off La Hopital's rule from yesterday's lecture. So on Monday, I'll give a Mobius revision lecture. So join me, M12A balanced. Okay, so join me for that. I hope you're doing well. Just to remind everybody that you have a lab test next week. Okay, so the details are on Mobius or on Moodle, and the best advice that I can give is to practice. Just do the practice test. There's no surprises. Everybody usually does very well in the lab test one. You should aim for 100%. Hi, Michael. Thanks for joining us. So today's lecture is about L'Hopital's rule, and then we'll talk about inverse functions. So let me know what's going on in the chat. I see we've got about 29 people here. So what I might do, I might just unmute everybody, and that way people can talk if they want to. Let me just see. Session settings. Here we go. So if you want to, you can share your video, you can share your audio. You should have that capability now. All right, so L'Hopital's rule, it looks like L'Hospital's rule, but hopefully it doesn't cause any injury. This is a way of taking limits where you have these indeterminate forms, right? So and it's hard to work out what these things actually mean, right? So the basic idea is that you differentiate the top, you differentiate the bottom, and you retake the limit, provided the limits exist. Okay, so L'Hopital's rule is pretty easy to apply. We're not using the quotient rule for differentiation. What we're doing is we're differentiating this function independently, differentiating this function independently, and retaking the limit. Okay. Now here, the A, it could be plus or negative infinity. So x might approach positive infinity or negative infinity. The idea still can work. Okay. So most important thing, these are the conditions. You differentiate and retake the limit. So this is usually best understood when we do some examples. Okay, so let me bring this in, and we can see how this works. All right. So the first thing is, well, okay, let's have a look at this function first. If we put in the value, so x equals 0 in here and here, we'll get 0 over 0. So we do have this kind of indeterminate form, right? Okay, it doesn't mean anything. We don't actually know what this is, but what it does say is that we can have a go at applying L'Hopital's rule provided all the limits exist. Okay, so this does satisfy these sort of conditions. So I'm going to apply L'Hopital's rule, the hop for short, and we can use this thing here. So I'm going to differentiate the top, and I'm going to differentiate the bottom independently of each other. And now what happens? Well, there's no problem with the denominator anymore. I'm not going to be dividing by 0 like I was up here. So what I can do is I can just put the 0 in. Okay, so the first step in applying L'Hopital's rule is to check you've got the conditions being satisfied. Differentiate the top, differentiate the bottom, and take the limit. Now, sometimes you need to differentiate more than once, right? So you might get to this stage and go, oh, I've still got this or this. Well, you keep differentiating. Okay, you can apply L'Hopital's rule more than once. Okay, so it's a pretty easy concept to apply, but what most people have troubles with is they don't know when to stop, and they apply the L'Hopital's rule when the conditions are not satisfied. Okay, so who can tell me in the chat what is this actual limit? Like, without doing any calculations, what do we know that this limit should be? Who can tell me the second part? Abdul Rahman says 0. Remember, x is approaching 0. It's a good guess, but not correct. Nicholas says undefined. Well, let's see what the chat says. Azalea says 1. I think you're correct there, Azalea, but let's actually find out, and by applying L'Hopital's rule. So let's put in 0, and that gives us this kind of indeterminate form, right? All right. And so let's again apply L'Hopital's rule. We differentiate the top, we differentiate the bottom, and we take the limit. So Todd also says 1. So let's see if we can do it. So the derivative of sine x is cosine x. And the derivative of x is just 1. So the limit now is going to be cosine of 0, which is 1. Okay, so some of you might have learnt this limit at school, and you would have done some geometry to show it. But you can see L'Hopital's rule is much faster. Okay, you don't have to draw a picture. You just differentiate and take the limit. Okay, last one. This one looks a bit weird because it doesn't look like a quotient. But what you can do is rewrite this and be a bit sneaky and write it like that. So this would be your top function, that would be your bottom function. So don't be scared to rewrite your functions in some kind of quotient, and you hopefully you can get this indeterminate form. Okay, so let's do it. So the natural log of 0 all over 1 on 0. Okay, well, natural log of 0 is going to be negative infinity, and this is obviously going to be negative infinity. So even though there's a negative sign there, it's still an indeterminate form, right? So you can have sort of plus or minus infinities here. They still count as indeterminate forms. Okay, so let's apply L'Hopital's rule. You're probably seeing a trend now. We'll differentiate the top, we'll differentiate the bottom, and we'll take the limit. Okay. All right, so let's see what we can do here. If I differentiate log of x, natural log of x, I get 1 on x. If I differentiate 1 on x, I get negative 1 on x squared. So now it's just a matter of cleaning this up. So we can cancel off some of the x's, and you end up with this. So what's the value of the limit? 0. Okay. So note, you may need to apply L'Hopital's rule more than once. Okay, I haven't done an example like that, but you might get to this stage and you've still got an indeterminate form. So again, you differentiate the top, differentiate the bottom, and take the limit. Okay, there you are, Jun. Yeah, it's a bit hard for me to do that. There you go. So Junsheng, have you got the, you should be able to download the notes, right? Okay, Abdul Rahman, good question. What is 0 divided by infinity? Right, 0 divided by infinity would, you would sort of interpret that as 0, right? So, and infinity over 0, well, that's going off to infinity. So, yeah, so the answer to your question, which is a good one, is no. Okay, so there are these questions, and let's actually look at some of the limitations here. No pun intended. The limitations. Oh, bad. That's bad. Why can't L'Hopital's rule be used to evaluate the following limits? Yeah, Alan, that's the joke. Ha ha ha. Why can't L'Hopital's rule be used to evaluate these two limits? Okay, now no, in this case, this one's going to 0, this one's going to infinity. So who can tell me on the chat, why doesn't L'Hopital's rule work for this? Can anyone suggest something in the chat? Yeah, if we put in, good work, Dijant. If we put in 0 here, that's like 2 on 0, which obviously is, it doesn't have this form. Right? Yes, Azalea is correct as well. Okay, so that's obviously not of this form. And for B, what's the problem with B? Who can tell me? So the bottom bit is 0, but what about the top? Sorry, the bottom bit's infinity. What about the top bit? It doesn't make sense, right? What is that? So this doesn't work because sine just oscillates. Okay, so the thing is neither of these satisfy the conditions of L'Hopital's rule. Okay. Well, Carl, you don't know what this is, right? I mean, it could be any value between +1 and -1, right? Yes, Azalea. Yes, it is possible to use L'Hopital's rule when x approaches positive infinity or negative infinity. Yes, it's possible to do that, and I've sort of said that over here, right? Yeah, Nicholas, the answer for this is obviously 0, but you can't get there by using L'Hopital's rule, right? You can't get there by using L'Hopital's rule. So you can do it using other ways of doing it, like squeeze or pinching theorem, but L'Hopital's rule won't help you here. Okay? All right. So let's move on to inverse functions. That's really the subject of today's today's lecture. All right. So goodbye, L'Hopital. Hello, inverse functions. Now, some of you will have seen this stuff at school, but some of it will maybe be familiar, but not all of it will be familiar. Okay, so that's the idea for the rest of the lecture. I was wondering where your avatar was, Nicholas. Love the quokka. All right, so we'll talk about functions and their inverses, the vertical line test, increasing functions, and this is probably new. Okay, this is probably new. This is a pretty interesting idea, but I'm sure some of you will have seen these things before. If you haven't, don't worry about it. Don't worry about it. Yeah, Nicholas, I told my family that somebody had a picture of me as their avatar, and they were shocked. They were shocked. All right. So inverse functions, we talked about this a few lectures ago, I think very early in week 1. But if you've got a function f, you can define the inverse by this function. And what the inverse does is it cancels out or does the opposite of what the function does. So if you have a function f and you combine it with its inverse, then these two parts cancel out and you're just left with the x, the input. Okay, that's the easiest way of understanding it, right? And so we're going to look at how to calculate the inverse of a function and the domain and range, ways of showing that you actually do have an inverse, and then a little bit of calculus. Okay, so let me have a look here. I'm just going to grab my notes. So just give me a second. Yep. Yeah, here's a really simple example. Suppose this is a function of x, and we're told that this is actually the inverse, right? So let's actually just check that to make sure it's correct. Okay, so if we do this, we want to put this in for x over here and see what happens. Okay, so now we simplify this. The 2's will cancel. So f of the inverse just gives us x. So similarly, and I won't do that here, you can check this. The opposite sort of order also gives you x. Okay, so that's a pair of a function and its inverse. How do we actually calculate these things, and what's the relationship between the domain and the range? Now, so let's talk about this first. We just have to be really careful when we talk about domains and ranges of the inverse. So the domain of the function is equal to the range of its inverse, and the range of the function is equal to the domain of its inverse. Okay, so this is best kind of illustrated through a picture, but let's do an example, and then I'll show you a picture, right? So if this is our function, calculate the inverse and the domain and the range, right? So what many people do here is just to exercise in algebra, right? So let's start off with this. We'll make x the subject. So natural log of y, we're assuming that these are all well defined. Okay. And now let's just isolate the x. Okay, so we take that and then just swap the x's and the y's. So instead of having a y here, we have x. All right, so that's just algebraic manipulation, really, and we're, that'll work for simple functions. But what does this look like, and what about the domain and the range? Well, let's go to GeoGebra. Did somebody say GeoGebra? And we can have a little look. Okay. Russell, so you basically from the definition of the exponential, the two equations are equivalent. Okay, so when I go back to my PDF, I'll discuss that in a second. All right, so there's e to the x. There's the function that we just calculated, and hopefully you can see there's a nice symmetry there, right? Okay, so that's the line y equals x, and the green curve is reflected in the red line to get the blue curve. Okay, so when you're trying to draw, if you want, or even just have some idea of what the inverse looks like, you can always plot the function and reflect it in the line y equals x. Okay, so that's one of them, which is pretty cool, right? Which is pretty cool. So here's another one, 3x plus 5, and the inverse is there. So you can see again, the grey curve is reflected in the red curve to get the brown curve. Okay, pretty cool, right? All right, so yeah, so let's go back to my PDF, Chrome tab. Sorry, that's the right one. So all I've done here, Russell, is taken the logarithm, natural logarithm of both sides. Okay, so the log and the e cancel out, and the 2x comes down. Oh, sorry, hang on. Let me try that again. All right, there we go. So all right, so what I've done there, Russell, is I've taken the natural logarithm of both sides, and the log and the e cancel out. Okay. All right. So yeah, thanks, Azalea. Good job. Yeah, Alan, inverse functions, they are essentially the same. Here we're just looking at mappings between sets of real numbers. In discrete math, you'd be just looking at sets in general, Alan, okay? So here we're interested in functions of real numbers. All right, so that's the first thing. What about the domain and the range? Okay, so the domain of our f, what is the domain of our f? Well, if that's our function, the domain is just the whole real line, right? We can put any x value into that we like, and we'll get a nice output. So what does that mean the range of the inverse will be? Well, the range of the inverse will also be the set of real numbers by this relationship here. Okay, what is the range of our f? Okay, the range of the exponential can never be 0, and it's always positive. And so this will be the domain. Okay, so once you have these two things, you immediately get the domain and the range for the inverse. And if you went back to the picture that I just showed you, it's very easy to verify these things, or convince yourself that yes, this is actually correct. All right, so sometimes we can calculate the inverse function. A lot of the times it's not possible, but this one was simple enough to do it. These are the important relationships between domain and range of the inverse and the original function. You just need to be careful. I think the important word there is really careful. Just be careful with it. All right. Okay, so when do functions have an inverse? We can't always calculate them. It's not always possible. And the most important information is that one-to-one functions always have an inverse. So we talked a little bit about one-to-one functions earlier. One-to-one functions, you might have forgotten, but that's okay. One-to-one functions, they might look something like this, right? And we're going to talk about a horizontal line test where the horizontal line cuts the curve at most once. Okay, that would be an indication of this one-to-one function. If I have a function like that, that's not a one-to-one function, because if I draw these horizontal lines, they cut the curve at two places. What that means is for two different inputs, they give you the same output. That's not okay when it comes to inverse functions. Okay, so this is the that's like the pictorial representative. This is sort of one-to-one, and this is not one-to-one. Yes, right, Steve. If you know about injective functions, you can also use that. A function f is to be one-to-one if no two elements in the domain give you the same output. So you can see here, these 2 points, they're different and they give you the same output. Whereas here, if you have a point here, you get that point. You have a point there, you get a point down here. So this is a bit of a mouthful, but it's just easy to remember, or just draw a picture. Okay, so for this one, let's just have a look. Show that this function is one-to-one. Okay, so f is one-to-one because no output. Hang on, let me rephrase that. So no two different inputs give us the same output. So that's a way of just putting it into words. We'll find a pretty easy test for this. And h of x so just the opposite, two different inputs give us the same output. So let's look at an example. Let's say x equals 2 and negative 2, right? So f of 2 will equal 8, and f of negative 2 will also equal 8. So that breaks that definition. Okay, or you can just draw a picture. That's pretty easy to do. Okay, so this is a bit wordy. I quite like the idea of pictures. So there is a test called the horizontal line test. Okay, so this is very similar to what's the same as what I've done up here. Okay, so the horizontal line test is an easy test, and it involves a diagram. And like the name of the test says, it involves a horizontal line. Okay, so the idea is draw a graph, and a function is one-to-one if and only if every horizontal line cuts the graph of f at most once. So let's draw these in GeoGebra, and we can see which ones are one-to-one and which ones are not. Okay, so this is a cubic, this is a linear function, and this is a quadratic or a parabola, something like that. Okay, so let me go up here and I'll go over to GeoGebra. And it should be sharing in just a second. Sometimes it takes a while. So that's our function. Okay, so who can tell me, is this function one-to-one everywhere? Who can tell me in the chat? Smash that chat button. Okay, lots of no's. And the reason is, if I was to draw a line here, let's say y equals 4. Here's a horizontal line. You can see it cuts the graph at 3 points. So you're all correct. It isn't one-to-one because it fails the vertical line test. Okay. Now you might say, well, Chris, what about y equals 8? Hang on, let me do y equals 9. That only cuts it at 1 point. Yeah, sure, but we can form another line where it cuts it at 3 points, right? So that's not allowed. Okay, so the first one would be no. What about, who can tell me, 2x plus 6? Does that pass the horizontal line test? Russell says yes. Alan says yes. Okay, if I put in any horizontal line, it's going to cross it at most once. Okay, so that passes the test. That's one-to-one. What about this one? Does that pass? Ronan's made a good question in the chat. I'll get to that in a minute. Does this pass the horizontal line test? No. So let's talk about your question, Ronan. What happens if I do this? Bum, 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 bum. That is just part of a quadratic. Does that pass the horizontal line test? Who can tell me? Does that pass? Yes, it does. So to get back to your question, Ronan, you can have a function that's one-to-one just on a certain interval. So this one is one-to-one for x greater than or equal to 0. Okay, and this one is definitely one-to-one for x, say, greater than 4, for example. Okay, because if so for x greater than 4, this is definitely a one-to-one function, but it's not one-to-one everywhere. Okay, so coming back to our document camera, this one, that one fails. This one passes. This one fails. Okay. And I'll just quantify that just by saying we're looking on the whole real number line here, okay? We're not looking at subintervals or anything like that, but we will in a minute, okay? We will in a minute. We'll do some questions. Okay. So all one-to-one functions will have an inverse. That's pretty important, right? All one-to-one functions will have an inverse, and that's the subject of the next slide. All one-to-one functions will have an inverse. That is super important. Okay. So let's have a look at the idea. Every one-to-one function has an inverse, and there's only one of them, right? Okay, and so let's apply what we've learned to an example here. I've sort of left some space on the other page which you might want to use. Okay, so here is our function. We're asked to do 6 things. Explain why f inverse does not exist on the whole of the real line. Okay, so who can tell me in the chat, how might I explain in a few words why the inverse doesn't exist on the whole of the real line? Who can smash something out for me? Why doesn't this have an inverse on the whole of the real line? Who can tell me? Smash that chat button, people. Yep, it's a parabola. Russell, the function fails the horizontal line test. Exactly. Exactly. I agree, right? It isn't one-to-one. So you're all correct. Okay? So if I was doing this first part, I would say something like f is not one-to-one on R. It fails the horizontal line test. So F inverse doesn't exist. Okay? So now they want us to go a little bit further and say, restrict the domain of this function such that f is a one-to-one function g that does have an inverse. Okay? So I showed you a picture of this before, but let me go back to it because I think it's important. Yep. Okay. Yes, Steve's on the chat with a good suggestion. So let me go here. So here's the function and part of the graph. So it'll just, so here the function's the same, but I'm restricting the domain to x greater than or equal to 0. You could have it as negative if you wanted to, but this is enough, right? So this function will definitely pass the one-to-one test with the horizontal lines, yeah? And so that's an example of a function that we could use. Okay, so for for part B of this question. Okay, so so that could be A and B. So I'm going to define this to be my function. Okay, so I've restricted the domain just to non-negative values of x. Great. Our g is one-to-one, and so the inverse must exist. Okay. Sketch the graphs of g and its inverse. Okay, so let's have a look at that. And what I might do, I'll just put that into this, into GeoGebra. So here it comes. Yep. So I've just used the invert command, but it's not too hard to rearrange this, right? So there it is. Okay, so it's the square root of x minus 7 on 2, and you can compute that using the same ideas that we did in the very first example where we had exponentials and logarithms. Okay, and so have I got x? There we go. So you can see there's that beautiful symmetry between so the inverse is this function here. Okay. Great. So I've drawn that on GeoGebra, and this is the inverse. We just need to now pay a little bit of attention to the domain and the range of each of our functions and the inverse, okay? So the domain of our original function is just here. And we know by our previous slide that is just the range of the inverse. Okay? Now, who can tell me what is the range for this function? Who can tell me in the chat? Smash that chat button. Who can tell me? You can kind of see it here anyway, but what is the range of this function? Yeah, Azalea, great. Thank you. And that's got to be the domain of the inverse. Yay. Sweet. So we work smarter, not harder. We don't calculate 4 things. We calculate 2 things. Wow. 2 things. And we can use them for the inverse. Brilliant. All right. Last thing. We got that from GeoGebra, but let's actually go through and do it by hand. Oh yeah, HN. That's exactly what we're going to do, buddy. So E is exactly how you get the inverse. Okay, so in this step I just used GeoGebra, right? But let's do it by hand. Okay, is that okay? Okay, good. So our function is here. So let's do it by hand. So I'm going to let y equals 2x squared plus 7, where x is greater than or equal to 0. And what I'm going to do is rearrange to make x the subject. So I've moved the 7 to the other side, divide everything by 2, and now take the square root. Now, why do I want the positive square root there? Because you could have a negative square root. It's because of that. I know that x can't be negative. Okay? So now what we do, we just redo our notation, replace y with x. Okay? Understanding that x is greater than or equal to 7. Does that make things clearer, I-Chen? Let me know. Thank you. All right, last question. Show that the inverse of the function g is just equal to x. Okay, that's what they want you to show there. So that this combination is really going to give you what you want. Okay, so g inverse. Okay, so this is what they want. So g inverse of g of x. So we want to replace that with g of x here. So our g of x is up here. So it's just a little bit of algebra. So you can see the 7s are going to disappear. Sweet. And then the 2s are going to disappear, and you take the square root of x squared. And again, because we know x is greater than or equal to 0, then you don't need to worry about positive roots or negative square roots or anything like that. Okay. So we are happy. Gosh, I've got 3 smiley faces on the one page. I must be super happy today. Okay, so this is kind of very similar to a question you might get in your final exam. There's lots of different steps. They ask you to do like small things for each part, and when you collectively put it all together, it forms a question. Okay, thanks, Nicholas. Yeah, thanks. All right. So whoop. Two more ideas to discuss. All increasing or decreasing functions are one-to-one. Okay. Yeah, Dijant, that's correct. But what do you mean by sine inverse? We'll talk about that next week, Dijant. So you restrict the domain of sine inverse. Okay. So we'll definitely, it's a good question. We'll talk about that next week. All right. So suppose you have a function and it's an increasing function. So the graph might look something like this. That definitely passes the horizontal line test. And so forth, then it's definitely one-to-one, right? And what this example is essentially asking you to do is show that this is an increasing function. Okay, so how can you do that? Well, you differentiate it, okay, and show that the derivative's positive. So let's differentiate it bit by bit. And that's positive, that's never negative, and that's never negative. So it's an increasing function, one-to-one, and thus F inverse must exist. Yeah, horizontal lines are interesting. Definitely not with the horizontal lines. That's interesting. So yeah, so you can't do it with the vertical lines, Abdul Rahman. If you had a vertical line, right, that gets you, like, you have the same sort of input and it gets you lots of different outputs. So you're right. So this, I mean, if you look at it, this looks like it would pass the vertical line, the horizontal line test, right? Okay, so what do people think in the chat? What about vertical or horizontal lines? Okay, horizontal lines definitely do not pass the horizontal line test, right? But the vertical line does pass the horizontal line test. Okay, so have a think about it. What do you think, Abdul Rahman? Let me know in the chat. Okay, let me know in the chat. So I think the horizontal line test definitely won't apply to horizontal line, but a vertical line's a different story, right? Yeah, Hira, the horizontal lines are not one-to-one. You're absolutely correct. Okay, horizontal lines are not one-to-one. Right? Okay. Last idea for today's lecture. Okay. A little bit of calculus. This is called the inverse function theorem. Okay. Okay, the inverse function theorem. So what the inverse function theorem allows you to say is that, well, suppose I want to differentiate the inverse. If I can't find it, how can I do that? Well, you can do this. You can use this formula, okay, and you can prove it by using the chain rule. All right. So this is a really interesting idea, and if you differentiate both sides of this, so you know from the inverse, this will give you 1, and this will give you this thing. So you can make your substitutions if you want. And then you just rearrange. Okay. All right, keep going in the chat, everyone. I'm loving the questions. Right? I'm loving the questions. All right. So, questions. Yeah, correct, Azalea. Vertical lines are not technically they're not functions, right? They're relations. Yeah. All right. So this is a very standard question that I'm going to leave you with today. Okay. You've got a function like that. You cannot compute, or it's very hard to compute the inverse function of that f. Okay. It's almost impossible. But what you're asked to do is show that the inverse exists and then evaluate this. Now, just make sure you've got a negative 1 here. I think in some of your notes, it's positive 1. Negative 1 is what you want there. Okay. All right, so the first part, show that the F inverse exists. So what I'm going to do, I'll just show you how to do this. I'm just going to show it's an increasing function, right? So let's go over to the window, and here is our function. Okay, you can kind of see that it's definitely an increasing function. It's a bit wobbly, but it's an increasing function. So what I'm going to do is show that the derivative is positive for this one, and that means it will be an increasing function. So if I differentiate this, I'm just going to put that underneath so I don't go through. I know that this is always going to be positive. Why? Because the most that sine x can be is 1, and so this is always going to be bigger than 0. Okay? All right, so it's increasing. It's got to be 1 to 1, and then it's sorry if I differentiate. Oh, sorry, hang on. Boom, there we go. Positive sine x. All right, so again, it's still positive. Thank you for letting me know, Eloisa. Okay, so it's positive. The derivative is positive. Great. So hence f inverse must exist for all the real line. Okay, so that's the first part taken care of. Okay, assuming you can differentiate correctly. Now, so what about this thing? This thing is harder than it looks, and it's a little bit of algebraic manipulation. Okay, so let's see what we can do. So the derivative of the inverse at -1. Okay, so we know from the previous slide that we can just use this formula using the chain rule. Okay, so really what we want to do is work out that. Okay, once we've worked out that, we can stick it into the derivative of the function and work it out. All right, so I'm going to introduce a little bit of notation with this. So I want to find z. So if I rearrange that, I want to find the value of z that makes this equal to -1. Now, usually these are simple things, right? Who can give me a value of z that makes this equal to -1? Who can give me a value of z such that this equals -1? Abdul Rahman is correct. Thank you. Okay, so that's the trickiest part of solving this. You've got to come up with some sort of value that simplifies this. Okay, so all I need to do now is put in 0 into the it's a half. So just think about what we just calculated. Yeah, we calculated the derivative of the inverse at that point, and we never actually calculated the inverse function. Oh my goodness, we didn't even calculate the inverse function. We didn't even do that. Okay, so we didn't actually need to calculate the inverse function. Woohoo, right? And so if I go over here, and let's say I tried to invert it with GeoGebra, it freaks out. You know, it actually can't do it. I don't think it makes it easier to compute the inverse function, Abdul Rahman, but we can definitely compute properties of the inverse function. Okay, so I guess what you might say is, well, if we can compute this, then can we integrate it or something like that to get f inverse? I don't think we can, but let me think about that. It's a good question. Oh, all right, everyone. It's been a long lecture. I fell a little bit behind with the L'Hopital's rule, but we've all caught up now. Nicholas, which slide do you want? Just give me the page number. But we're back on track. On Monday's tutorial, we'll do Mobius. Okay, we'll do Mobius. That's it. So yeah, hopefully I'll see you on Monday. If anybody has any extra questions, hit me up. We've got a few minutes now, so let me know what you're thinking, or if anything's unclear, or if you want me to repeat anything, let me know, everyone. If not, I will sign off, and yeah, have a great weekend. TGIF. Exactly. See you, Azalea. Thank you, Alan. Brett. Abdulaziz. Thank you. Nicholas. Aiden. Steve. Have a great weekend. See you Monday for Mobius. See you, Chief Carl. Meng Lu. Take it easy. Mobius. Yeah, Mobius Monday. Maybe we should call it Mobius Monday. But have a good one, and yeah, I'll be here for a few minutes.